So we've made this nice dust source to emit the dust from our destruction sim here. And now before we start simulating this, we also need to make some collision volumes. So we need to make colliders for the destruction fractured pieces and the creature that's flying through it and the ground as well around the destruction area. So let's start with the animated collider objects first. So let's merge those in. I'll drop in an object merge and point this to object slash destruction slash simmed destruction, which is our simulation scale of this sim. It's not the one that's been transformed back into world space for rendering. So if we display this, you can see it's in the same simulation scale as our dust source is. And now let's also object merge in the creature. So in a second object merge, let's point this to object slash creature flying simulated and out squid3. Then let's merge these together. And actually, the creature is not going to be in simulation scale yet. If we hit space G to frame all of our visible geometry, you can see this squid creature is out in a different space. So I'm going to pin my viewport into this dust section here, and then just jump back to our destruction setup, and let's grab our simulation scale transform from here. And if you want to make this a bit more streamlined so you don't have to keep grabbing these simulation scale transforms, you could potentially add a simulation scale parameter to this control null at the object level here. We're currently only using that for some unified wind direction, but you can certainly add some things like simulation scales or whatever other global settings you might want to put there. But for now, I'm just going to stick with these transform stops that are putting things into the correct scale for a simulation. So let's drop that on the imported creature, and then you can see these are both in the correct space here. Now I'm going to unpack all of this geometry so we can get those raw polygons and get some per point velocity calculated on them. So if we middle mouse on the unpack, you can see it's all regular polygonal geometry now. Then we can drop in a trail and set this to compute velocity. And if you want to sanity check these velocities, we can turn on the velocity display in the viewport here. So when you turn that on and display the trail sup, then you can see all these velocity trails are looking correct, and we can go ahead and create a collision volume from this. Now, when we created a collision volume for the environment for the shockwave simulation, we just used the collision source sup. And if you go to the volume tab, this gives us some option for what the collision volume is called, and voxel size, and options to fill the interior of that volume, and etc. And on the geometry tab, this allows you to do some of that velocity computation here as well. But oftentimes, I prefer to just convert my geometry to VDBs directly. So instead of using this collision source, let's delete that and drop in a VDB from polygons. Connect that to our trail, and I'll set the voxel size to what I've been using for this simulation resolution, which in this case has been 0.08. So if you display that, that took a moment to compute. That's probably about 10 seconds of a computation for my machine here. And this is showing us an SDF VDB representation of our geometry. And in addition to this SDF that it's creating from that geo, we can also create additional volumes based on surface attributes like velocity. So under surface attributes here, hit the plus sign to add one. And then in the attribute dropdown here, you can select point.v. That's going to be the point attribute velocity. And for the vector type, I'll set this to displacement slash velocity slash acceleration. And we can also specify the name for the VDB that's created from this attribute. So if you middle mouse on this, you can see this is currently called V for velocity, just like our geometry attribute was. But if you need to, you can put in a different name here. Like in some cases, you might want to call this collision vel. However, this is something you have to be very careful about when using the Pyro solver. So let's drop in our Pyro solver here. And just to keep things nice and clean, I'll drop a net box around our dust source here. Rename that accordingly. Bring our colliders down here, and we're not going to connect everything up to the Pyro Solver just yet, but if you select this Pyro Solver, and then scroll down to the collision section under the setup tab here, I pointed this out in the shockwave setup, but this can either create a collision source from the geometry that's passed in, or it can use the SDF and volume velocity that you're passing in on that second input. So when we created the collider for the environment in the shockwave sim, we used a collision source SOP, and on the volume tab, this volume name is defaulting to collision, and that's what this Pyro Solver is expecting for this SDF here. But this isn't necessarily very obvious. This is something that you would have to look into the help docs to really make sure that you're using this option correctly. So you can hover over this parameter and hit F1, and that will bring up the docs for the Pyro Solver here. And under collisions, if you look at this create from option, this tells you that, this collision source will build those collision volumes from that geometry in the input. And as I mentioned before, the SDF plus volume velocity option can give you better results. The docs also point out that this can provide the fastest and cleanest setting of collisions because you're really accurately controlling exactly how these volumes are constructed. But in addition to that tip there, they also point out that that second input of the Pyro Solver here is looking for volumes with very specific names. The collision volume has to be called collision, and the velocity volume has to be called V. And in the past, it's been very common for collision velocity volumes to be called collision vel, and if you're used to that workflow and not aware of these naming requirements, then that's something that could easily cause problems for you. So we want our volumes to be called collision and V. So if we take a look at what we're getting out of our VDB from polygons here, the velocity is called V, so we can leave that as it is, but the SDF is just called surface. So on our VDB from polygons here, under the distance VDB, we can change the name from surface to collision. And after making sure this is set correctly, we can go ahead and cache this out to disk. These collision volumes are a little bit slow to generate from all of that animated high-res geometry, so I definitely would suggest caching out this collider object and not just letting this be passed straight into the solver without being cached first. So let's drop in a file cache. Under the destruction directory, create a new dust collide directory and call this dustcollide.f3.bgo.sc. And you can run this across the entire frame range from 1 to 240, but because we're calculating velocity, we have to be a bit careful here. On this trail SOP, the default velocity calculation is backwards difference, which means it's comparing to the previous frame. So we need to make sure that we have geometry available on all of the frames that are being cached out. So if we go back to frame 1, let's make sure that nothing will error out here. And sure enough, it looks like we are getting errors because we don't have geometry prior to frame 1. So let's step forward one frame to frame 2 and check that. So frame 2 looks totally fine. We have all of our destruction and creature geometry visible here. So you can either change this to cache from frame 2 instead, or you could drop in a time shift, and we could drop this in probably anywhere here, but I'll just go ahead and drop this right before our file cache. And then on the time shift, you can leave the frame parameter alone and then set the clamp to first. Control Shift click that start frame and change that to 2. And if we display that, let's double check the start and end frame of our shot just to make sure we're not getting any errors. So frame 1 is fine now. It's just a duplicate of frame 2, which is totally fine for our purposes, and we won't get an error when running the file cache on the entire shot. And we can also check the final frame as well. So frame 240 looks all good. We have all of our geometry available here. And now that we've fixed that first frame error, we can go ahead and hit load from disk and cache this dust collider out. Now we've cached out this volume collider for the entire frame range, and this took a little bit over 40 minutes on my machine, and this really highlights how beneficial it can be to run these intermediate caches. If we just ran this volume collision setup into our Pyro solver without caching it out, then that 40 minutes to generate these collision shapes would be added to every iteration of our dust simulation, and we definitely don't want that. Now, when we went over the Shockwave sim, I talked about how the velocity can cause some undesired results in the simulation if you're pumping too much velocity in there. And when you're doing normal velocity sourcing, if you take a look at that sourcing tab, we have this scale option to turn down the velocity. But with the collisions, we don't have that same sort of control. We don't really have a multiplier for that collision velocity here. And we do have to watch out for the collision velocity values as well. So to adjust the collision velocity, we can just drop in a volume wrangle after our cache here. So type in wrangle, drop in this volume wrangle here, and connect that to the cache. And this is different from our normal attribute wrangle. With an attribute wrangle, this is set to run over your geometry. It runs on points or primitives or on the entire geometry input all at once, but the volume wrangle is a bit different. You can see we don't have that option to tell it what to run over, and this is just going to modify the values in the volume directly. And it's worth pointing out that if you look at the list of different types of wrangles here, the point wrangle and primitive wrangle and vertex wrangle are all exactly the same as the attribute wrangle here. If you select any of those, you're really just dropping in an attribute wrangle SOP. It's just setting up this run over parameter based on whichever version you chose. So those few wrangle types are the same. And this volume wrangle is different, and that's the one we want in this case. So in our volume wrangle here, I'll call this vel mult. This will add a multiplier on our velocity, and I can say at v times equals 0.1. And this is going to multiply down our velocity to 10% of its current value. And if you want to check what's actually happening to the values in your volume, we have a couple tools that we can use to check this. So first, let's just isolate this velocity volume. So drop in this blast SOP, and under the group, select at v, flip it to delete non-selected, and display that. I'll call this isolate velocity. And the velocity looks a bit weird when you just look at the default view of this volume. This sort of fog display doesn't really have any good way of representing these velocity vector values. Those velocities are really just directions with a magnitude, and we don't have a meaningful way of representing that with this sort of default display here. So we need to look at this in a different way to see what's going on in there. One tool that we can use to look at these values is the volume slice. So if you drop that in and connect it to our isolate velocity here and display that, you can see this is creating a plane running through our volume here. And you can move this offset parameter around to change where this slice is happening in your volume. And all of the points on this plane here are going to pick up the actual values from the volume. Now, if you look at the attributes on this volume slice plane, you can see we don't have an actual velocity attribute because the attribute that it's setting those values on from the volume is specified in this parameter here. See, we have this attribute parameter, and it's just calling this density. So let's open up our spreadsheet for the volume slice and scroll over to density. And because we're running a vector velocity volume into our volume slice here, that's why we're seeing a vector density value here. And this isn't really density in a meaningful way. It's just the name of the attribute. We can change this to something else on the volume slice parameter there. We could change it to V to match what we're actually sampling with the slice, or you could just set it to whatever you want. I'll just call it test. And you can see there's a lot of values of 0 in here, but we do have meaningful velocities in there as well. It's just that most of the points that are sampling this volume here are not actually, picking up any velocity values. So it's to be expected we would have a lot of 0 values in there. But you can see we have all of these velocity values picked up on that attribute. And if we bypass our velocity multiplier here, you can see those sampled values changing accordingly. And you can see the amount of velocity in the volume is really only 10% of its original value after it's been run through that wrangle. So this is one very helpful way of debugging what's going on in your volumes. And this still doesn't really give us a good look at what the velocities are actually doing. So another way that we can take a closer look at these velocity values is by using the volume trail SOP. And this volume trail requires points in space to generate those trails, and to generate those points in the right areas, we can base this on the collision volume. So I'll drop in another blast, connect this to our vel-mult wrangle, and I'll call this blast isolate collision. And then in the group here, I'll select that collision volume, flip this to delete non-selected, and display that. And now we can use a pyro source to fill that area with points. So if you drop in that pyro source, connect it to our collision volume and display that. This isn't showing us anything just yet because the mode is set to keep input, but let's change that to volume scatter. And this is going to fill the entire volume with points here. And this is quite dense. This is generating almost 2 million points, and we don't need nearly that many for our visualization purposes. So let's change our particle separation here. Let's turn that up to 0.5. So we're not generating nearly as many points now. And we can connect this to the first input of our volume trail, which says that's the points to trail there. And in the second input, we'll connect that to our velocity volume and display that. And this gives us a good visual indication of what's actually happening with those velocity values. And this is particularly helpful when you're doing some more work in SOPs to really build some interesting velocities that you want to add into your simulation. And you can even modify these existing velocities if you want to. For example, if you didn't really want to inherit these sort of clean, straight velocity lines here, if you really wanted to break that up a bit, you could break that up with some noise with the volume velocity SOP. So if you drop that in, connect that between our velocity volume and the volume trail here, and then go to the curl noise tab and turn on add curl noise. You can see this is really adding a ton of noise to our velocities here. And on this volume velocity SOP, we can tweak this a bit. Perhaps we don't want it to be so high frequency. We could turn up that swirl size, try a value of 3. That gives us some larger scale swirls. Maybe turn that up a bit more. And this is still quite aggressive, so you can control the amount of noise being added as well with the scale parameter here. So if you turn that down, this is really just adding a bit of wavy breakup to those velocity directions. So this can be a pretty powerful way of controlling the velocities in a very manual way. In our case, I don't really think we need to mess around with this. You can feel free to experiment with breaking up these velocities if you'd like, but for this simulation, I'm just going to leave it on, the standard velocity that's being inherited from that animation. And just a quick word of warning, when you do this sort of volume trail visualization of the velocity, make sure that you're adding the velocity volume itself to the simulation. If you middle mouse on it, you can see this is just a volume here. I've seen a lot of people make the mistake where they've set up a volume trail for visualization, and then they've added in the volume trail to their simulation, and then wonder why it's not working properly. This volume trail here is not an actual volume. It's just showing us a polygon display of what the volume data is actually doing. So this volume trail output is useless to a PyroSim. Make sure to add the volume itself. But in any case, this is really just for investigation and visualization purposes. So I'm just going to drop a netbox around this, call this visualize velocities. And we can just use our animated colliders after they've been multiplied down without really doing any extra manipulation to them. So I'll drop in this null and call this collide animated. And now we can go ahead and set up some terrain colliders for the surrounding areas as well. And now we can reuse some of the setup from our RBD destruction colliders for our volume collision as well. So if we go over to our destruction setup here, you can see that for the ground collider here, we've merged in the static region of the terrain that has this, the destruction region cut out of it here. And then we're also bringing in that area of interest, scaling that up a bit to define the areas that we need to collide with in our rigid body sim, and then doing a Boolean to cut out that area. So we can just copy the same setup here and go back to our dust setup and paste that in. And perhaps for the dust collision, we might want to expand this a little bit wider than for the RBD collision. It's up to you to determine if that's really necessary or not. But I'm going to start by dropping in an additional transform here. I'll template display that, use our centroid transform preset, and then use the uniform scale to expand this region a bit. And then on the Boolean, we had this set to a solid intersection for the rigid body collider setup. So if you display that, you can see this is giving us a solid chunk cut out of that terrain here. However, for the volume collider, we don't necessarily need to do this intersection as a solid. It could run a bit faster if we do it as a surface instead. It's up to you, whichever you prefer. But if you do that intersection as a surface, you do need to add some thickness to this for our volume collision. So in that case, you would add in an extrude volume and display that. And it looks like the defaults on this extrude volume should work just fine. And then to generate the collision volumes for this, we can use the same VDB from Polygon settings that we used for our animated colliders. So let's copy that one and then paste it down here underneath our extrude volume and connect that up. And if you display that, we now have a collision volume as expected. We don't have the velocity volume that we did with the animated colliders. And this VDB from polygons is trying to create a volume based on this point attribute V. We don't currently have it here. We probably don't really need that velocity volume for the terrain, but if you want to keep it consistent and add in this zero velocity on the terrain there, we can drop in an attribute create. I'll set the name to V. The size is 3 because it's a vector, and this will just write values of 0. And then I'll drop this in between the extrude volume and the VDB from polygons. And now if you check our VDB from polygons output, you can see this now has the velocity volume just like we had before with our animated colliders. So let's drop in a null on this. I'll call this collide terrain. And it's up to you if you want to cache out this single frame of this terrain collider here. It's not really as crucial as it was for the animated collider, because for the animated collider, we really didn't want to run this creation on every single frame of our shot. For this single frame on the terrain, it's not such a big deal, so that's up to you. But now we can just merge those colliders together, connect our collide animated and our collide terrain. and display that. So now we have these volumes merged together, and if you middle mouse on that merge, you can see we have 2 collision volumes and 2 velocity volumes. And that's just fine. Our Pyro solver is expecting multiple volumes on that second input for the collisions, so this works just fine. If we take a look at the Pyro solver help, you can see under this collisions create from section, it's looking for all of the volumes named collision and all of the volumes named V on that second input. So multiple volumes with the same name there are totally fine. So to keep everything nice and clean, let's drop a net box around our collisions here. I'll call this collision volumes. And now we can connect the source to the first input of the Pyro solver, collisions to the second input, and now we can go ahead and start setting up and running our simulation.